Thank you very much for your introduction. Good afternoon. So I'm aware this is the last presentation before the coffee break, so I'm going to try and keep it as light and as possible. So just to have a quick overview of what I'm going to talk about, I'm going to start with a brief introduction and background, and I'm going to present the objective of this work. And I will continue with displaying the experimental methods and statistical analysis I use. Then I will present the results of the work and conclude my presentation. So, aluminum is widely acknowledged as a sustainable material. First of all, because it allows to build lightweight vehicles, thus reducing emissions and fuel consumption. Moreover, the recycling process is much more or less energy intensive compared to the primary production of aluminum. So as you can see, let me see if I can. Okay, as you can see from this graph, the recycling process allows to reduce the emission by up to 95% compared to the primary production of aluminum. However, the recycling process presents some challenges, one of them being the accumulation of impurities, such as chemical impurities, for example, like iron, and non-metallic inclusions, such as oxides. So when these impurities accumulate, they compromise the mechanical properties of recycled products, leading to, for example, embrittlement and early initiation of fracture. So there are several ways to address this problem, one of them being salt fluxes, which is also the main topic of my PhD research. So what are they? Basically, they consist of chloride mixtures, mainly which act as fillers, fluidizers, and some active compounds, such as fluorides and carbonates, which tailor the properties of flux. Fluxes are used during the treatment of the molten metal, and they serve three main functions. They protect the molten metal from oxidation, they increase the metal recovery, and they help in removing impurities, thus leading to improved melt quality and cleanliness of the molten metal. So the objective of this work is to investigate the effect of using salt fluxes on the dispersion of tensile properties of a recycled aluminum silicon 9 copper 3 iron alloy. Under three fluxing conditions, so using flux A and flux B, which are commercially available fluxes but with different chemical compositions and no flux, and under two processing temperature, 720 and 760 degrees. Furthermore, Bible's statistical approach is widely acknowledged in the literature to investigate fracture-related mechanical properties. However, there is no evidence regarding the use of Bible's approach to the use of fluxes. So the research question is, how is the distribution of the mechanical properties affected by the use of fluxes? So let's move on to the experimental procedure and statistical analysis I used in this work. We started by melting 5 kilograms of aluminum scrap, and then when the metal was molten, we stirred the metal, as you can see in this video, if you could please play it. And in the vortex that was created by stirring, we poured the fluxes. Then we produced some tensile specimens by casting, and we continued with a Bible statistical analysis, both considering a 2-parameter Bible distribution, so by setting the threshold parameter equal to 0, and a 3-parameter Bible distribution, so by also considering this threshold parameter. The Bible analysis was performed on the elongation to fracture, which according to the literature is the most sensitive parameter to the presence of defects. Lastly, I concluded the investigation with a microstructural study using optical microscopy, and lastly with fracture surface analysis using SEM. So now let's move on to the results I obtained from the tensile tests. Let's focus on the elongation to fracture first, which is the graph you can see on the left. And what we can observe from a first sight is that the dispersion increases with increasing processing temperature here, while it decreases when fluxes are used, especially at lower processing temperatures. Whereas for what concerns the ultimate tensile strength, it did not significantly show an effect of either the flux or the processing temperature on the dispersion. Whereas the yield strength was not affected by the fluxing or temperature condition, as confirmed by a one-way analysis of variance, which produced a p-value of 0.79. Now let's move on to the two parameters Weibull distribution. From the first graph on the left, we can see that the higher Weibull modulus was obtained when using flux A, which also produces the narrower distribution, whereas not using the flux led to a lower Weibull modulus and thus to a wider distribution in the Weibull analysis. This effect is also encountered at higher processing temperatures, where you can see that the fluxes produce, again, narrower distributions, whereas not using the flux produced a wider distribution. So greater Weibull moduli values are achieved when using fluxes, especially at the lower processing temperatures, which of course implies an improved reliability of the castings when using fluxes. However, according to the literature, the threshold parameters should also be considered because it can provide valuable insights on the distribution of defects in castings. So now let's see the three parameters Weibull distribution. From these graphs, we can make three main observations. The first one is that we obtain a positive threshold, which according to the literature implies that there is no mixed Weibull distributions. So this also implies that there is an absence of different population of defects in the samples. Moreover, a narrow distribution was obtained when using fluxes again, especially at 720 degrees, which is in accordance with the previous two-parameter Weibull analysis. And lastly, the threshold parameter increases when using fluxes, which also implies that there is an increase of the value of elongation below which no specimen is expected to fail. So now how can we correlate the results from the Weibull analysis to the microstructure of our samples? Well, we can start at low magnification levels. So if we observe this micrograph, we can see that when no fluxes are used, so these two micrographs here, there is high porosity in the samples, which is translated into a wider distribution in the Weibull analysis. Whereas when fluxes are used, so these two lower micrographs here, lower porosity is encountered in the samples, which is translated into a narrower distribution in the Weibull approach. So of course, this again implies a reduced scattering and dispersion of the data, and therefore a higher reliability of the samples. But now we can further increase the magnification level. So we can have a closer look at the microstructure and specifically to some iron-bearing intermetallic compounds present in the microstructure of the alloy. And this will help us understand why the curves at 760 degrees are shifted towards higher values of elongation to fracture. If you take a closer look at the iron-bearing intermetallic compounds present in this micrograph, which are characterized by a darker color, you can see that the ones that are produced at 720 degrees assume the morphology of a needle, which of course lead to an embrittlement of the alloy, whereas at 760 degrees, these iron-bearing intermetallic produce a so-called Chinese script morphology. So this explains the shift of the curves to higher elongation values. Okay, now we can further increase the magnification level. and take a look at the fracture surfaces using SEM. So the fracture surfaces predominantly show a ductile failure, as indicated by the presence of dimples. However, there is also some zones to indicate the presence of brittleness, as indicated by the presence of cleavage facets. And lastly, we can observe that some oxide films were encountered on the fracture surfaces. So what conclusions can we draw from this work? Well, first of all, Fluxes allow to obtain higher values of fibril moduli in the 2-parameter fibril analysis, thus suggesting an improved reliability of the castings. Moreover, the threshold value obtained in the 3-parameter fibril distribution increases with the use of flux, thus, of course, raising the value of elongation, below which no sample is expected to fail. Then, high porosity levels in samples not treated with flux led to wider fibril distribution, whereas the needle-shaped intermetallic compounds shift the distribution towards lower elongation values. So for improved reliability and safety of the castings, flux treatment is necessary, as well as temperature control. And to conclude, the present study successfully employed fibril statistical analysis approach to assess the efficiency of using different fluxes on a recycled aluminum silicon 9 copper 3 iron alloy. Thank you very much for your attention, and I'm here to answer any questions.